I've been talking about the people who've been important to me here at St. John's. And so last time we talked about kind of the moderately important people like Newton and Maxwell, and here we've got the most important person for me at St. John's St. Ben's, and that's my wife, Ellen Jensen, who is a microbiologist here, and we met here and married here, and have so far lived happily ever after here, except for this COVID virus. Last time we were talking about intellectual backgrounds, and I checked out my sister. So she has not just Newton and Maxwell, but also Galileo. So you can also consider yourself connected to all of those people too. She's kind of got quality as opposed to quantity. I have a whole lot of pretty important people. So this is, of course, and let me also remind you that the course evaluation, you should have had a link to that. I want to encourage you to fill that out. We are interested in how this terrible semester has panned out for you, and maybe we can learn from it. So these are, of course, the main event for this course, Maxwell's equations, James Clerk Maxwell. And once we've written down Maxwell's equations, there are all sorts of things that we could do, and the rest of the book is filled with it. And I've been kind of cherry picking the things that are of particular interest to me. And so last time we were talking about how to calculate radiation. So you know that, let me find this kind of cheesy representation again. We know that we have, we know that we calculated last time that the way to make light is to accelerate charge. And here's kind of the picture you should have in your mind for how light is made. So we have a charge that's going simple harmonic motion, up, down, and it's releasing these electromagnetic waves. And the key feature to this is that acceleration is the source of electric fields. So we accelerate charge, and we got EM waves. And we went about showing this in somewhat kind of roundabout way. What the formula we were interested in showing, let me get back my cursor, is this guy, that q squared acceleration squared divided by speed of light cubed, this factor of 2, 3, and this factor out here that is basically has to do with units. This shows us the total power that's being outputted by an accelerated charge. This reminds us that the light comes out perpendicular to the charge. So in the direction of the acceleration, there is no, in the non-relativistic version of it, no light that is going to be emitted. It's only going to be emitted where perpendicular to the corresponding acceleration. And kind of the plan for the day is to pick out some sweet spots for this. Talk about the shadow that's left by an electron in terms of the Thomson scattering cross-section. Oh, there's no P in Thomson. Okay. And the approach we took, I guess the other thing I wanted to remind you of a little bit, and we're really not going to do much about this, is we could use this formula to calculate the energy that's radiated by a typical antenna. And as you might expect, the radiation depends on the amount of current that's flowing through the antenna in kind of the I squared R formula. And this is called the radiation resistance, and it's of order of the square root of mu naught over epsilon naught, which is 377 ohms. It will depend on the size of the antenna, and in a kind of standard setup, a half wave antenna, it's going to be 73 ohms. But the way we started out on showing this is, first of all, I had to, what we wanted to do is to solve these wave equations. So these are wave equations with sources. This quantity here is called the Dow inversion. And if we've got a right-hand side, then we can have the source of these waves that are going to propagate at a speed that is going to be 1 over mu squared epsilon mu. And it's kind of a lot of algebraic mess that we're avoiding. What kind of makes sense is that what we're interested in is not how the source is doing now, because it would take time for what's happening now at a distance to affect me. We're interested in what the source was doing at a time it would take light to connect us. And we made this argument based on a very simple model, where one-dimensional model where waves could only travel in one direction, and we had a very simple wave equation. So that was a start. Then we started to look at this argument, not really a calculation due to J.J. Thomson, and the upshot is the acceleration all happened in a relatively brief period of time here at the beginning, and since then the particle has been drifting at constant speed, and the electric field has been pointing away from it during that time. And before it was accelerated, the electric field was pointing away from its then current position, and somehow or other the electric field has to make an adjustment between these two directions. And we were able to calculate that and show in the end that the electric field was, that this electric field, this kink corrector, was proportional to the sine of theta, and it just fell off like 1 over r as opposed to 1 over r squared. So that was the key to proving that super important Lamier formula for the power lost by an accelerated charged particle. Okay, so that's kind of where we were. What we would like to do is to use this formula for some kind of useful purposes. And I have in mind a couple. One is trying to understand why the sky is blue. And another is to kind of understand what the shadow is of an electron. Okay, so if we're thinking about the Earth's atmosphere, and of course the Earth's atmosphere isn't blue, it's really transparent, but I've got this, actually I've got this color that you can't, there it is. There's the Earth's atmosphere. And we have the sun, which I'm going to use for black light, shining through it. And some of this light will be scattered down and into our eye. So here we have the incident wave that's coming in with a particular polarization. And I guess we really don't need names for these things, but let's quite naturally call this the z-axis. So this is light that's coming in on the x-axis, and it has an electric field that's in the z-axis. And we're interested in its effect on a typical atom. And what we've said when we were talking about polarization is we can think about the charges in material as being connected to simple harmonic oscillators. So it's of course not true, they're not literally connected to simple harmonic oscillators, but basically from Taylor series expansion, to first order, everything is a simple harmonic oscillator. So what we could say then is the acceleration, and we have some sort of damping force. I'm mostly going to ignore this, but let me put it in just for fun. And then we would have omega naught squared times r. All of this would equal the driving force, would be the charge times the electric field, and of course we've divided everything by mass. Now you might remember that there is a natural frequency for almost all material that's in the ultraviolet. Whereas the light we've been talking about is visible light, which has a frequency that is substantially less, maybe only a factor of 2 less, from these resonances that are in the ultraviolet. So what happens when when the driving force is at a frequency that is much less than the natural frequency? And if you think about it physically, what happens is that moment by moment, the spring, and let's go back to kx sort of stuff, kx is going to equal what that force is, right? Because the spring could respond very fast, and so the corresponding amplitude is just going to depend on the instantaneous value of the force, right? So again, the situation we're talking about is we're applying a force at a much lower frequency than the resonant frequency. So if we have a pendulum and you decide to push it at a much slower rate than it wants to, then what's going to happen is it'll be in equilibrium basically at all of these corresponding instances. Okay, so what that means is that the amplitude at any particular time is just going to be the force divided by this omega naught squared, right? And actually, of course, the omega naught squared has an m in it. They would cancel out, but it doesn't really matter. And of course, the acceleration is the second derivative of that. So that's going to give us an acceleration that is the ratio of omega to omega naught squared. And what we've learned is that the amount of scattered light, the power that's being radiated, is proportional to the acceleration squared. And so it's proportional to omega over omega naught to the fourth. So what this means is that the closer the frequency of the light is to the ultraviolet, the bigger the acceleration and the larger fraction of the light that'll be scattered. So if we're back to this picture, the light from the sun, of course, consists of all of the colors of the rainbow, but the blue light is going to be directed more frequently than the red light. Of course, it's not going to be particularly directed towards you, right? It's going to go in all directions. And the red light is going to also be scattered in all directions. But the amount of blue light is going to be more than the amount of scattered red light, and so we're going to have a correspondingly blue sky. Okay, so this is called Rayleigh scattering. It would apply to basically any molecule. Obviously, in our atmosphere, it's mostly nitrogen and oxygen, but it has nothing particular to do with the particularities, right? It's just relying on the fact that most all material has a resonant frequency that's in the ultraviolet. Okay, so let's now switch to a simpler case. And that's the case of a free electron, right? So if there's free electron, there's no velocity damping, and there's no restoring force. Okay? And what this means then is that the acceleration is just going to be QE divided by M, where this is the electric field that is being applied at whatever frequency it's going to be applied. And as you might guess, for shadows, the frequency isn't going to enter in. So what we've got then is the total power radiated is this 1 over 4 pi epsilon naught, and then we had this 2/3, and then we had the charge squared, the acceleration squared, and the speed of light cubed. Okay, so let's kind of plug and chug our way through this. So what we've got then is 1 over 4 pi epsilon naught, 2/3, and now what we've got is q to the 4th, the charge of an electron to the 4th, divided by m squared times the electric field squared, all times c cubed. Okay, so this is the total power in watts that are being radiated by this electron, which is being jiggled by the corresponding light. And the light is coming in with a certain amount of watts per square meter. So if we think about the electron as being kind of absorbing dot, how much of the wavefront is going to be eaten up by this electron? So that's kind of what we mean by the shadow of an electron. So this corresponding area is going to be this power divided by the S vector, right, by the number of watts per square meter. So watts divided by watts per square meter is going to give us square meters, the size of the corresponding dot. So what we've got then is the corresponding S vector. So let's kind of plug and chug our way through this. So we've got 1 over 4 pi epsilon naught, 2/3. Then we've got charge of an electron to the 4th, mass squared, electric field squared divided by c cubed. And the corresponding S vector we know as being 1 over mu naught c times the electric field squared. Right? It's really E times B, but E over C is going to give us the B. Okay, so we're going to get now pretty big cancellation. So the strength of the electric field is going to cancel. One of these C's is going to cancel. Now we've got a mu naught that is in the numerator, and kind of what we want to do is to have epsilons in favor of mu naughts. So let's rewrite it while we've got it. Oops, I guess I want to use a corresponding red pen. Okay, so I'm going to bring out the 2/3, and I'm going to bring out knowledge of forethought of 4 pi, and that means I have 2 4 pi's down here. And I've got a mu naught over epsilon naught, and I've got a c squared. Kind of see how that's going to work out. And then we've got the charge of an electron, which typically people use E for, so I'm going to switch to it, divided by the mass, all that quantity squared. Okay, and of course what we know is that mu naught is equal to 1 over c squared times epsilon naught. So what I've got here is 2/3, 4 pi, and now I've got 2 epsilon naughts, and I've got 2 c squareds, and I'm a happy camper. Okay, so let's see kind of how we can break apart this result. So we can see we've got all of this stuff squared. What's one of these things? So if we look at 1 over 4 pi epsilon naught, the charge of an electron squared divided by mc squared, how can we interpret this? Well, if we had a charge radius for an electron, then E squared over 4 pi epsilon naught, that would be the electromagnetic energy. Charge times voltage. And if 100% of that energy was the rest energy, we would get by bringing this rest energy down like that, this thing here would give us a radius, the so-called classical radius of an electron. Which is about 10 to the minus 15th meters, which is pretty small. So we can rewrite this if we want, and this is the way it was in the write-up, the classical radius of an electron squared. Now, I'm not really, classical radius of an electron is not the radius of an electron. Doesn't really have much to do with anything. So seemingly for no particular point, I'm going to want to put in some h bars into all of this. So what we have here is 8/3, and then we've got 1 over 4 pi epsilon naught, and we've got a e squared over mc squared, this whole quantity squared. Okay, so let me borrow one of these c's and put it over there, and borrow an h and put it up top. So what I've got then is h bar over 4 pi epsilon naught 4 pi epsilon naught c, and I'm going to put in an e squared there also. And what I have here is not what I want. I want h bar over mc. So I guess I put my h bar in the wrong spot here. I'm just going to borrow it and divide it, which, as I say, is just playing games. Okay, so this quantity here, thing out front, is called the fine structure constant. And it's usually denoted by alpha and has a value that is small. It's like 1 over 137. And it's unitless, so it's kind of an absolute measure of the strength of the electric field. This quantity here is something that is more closely related to the size of an electron, although I would say electrons don't have size. This is called the Compton radius. Unfortunately, Compton and classical both start by C. So another perfectly good way of writing this is h pi over 3 alpha squared, the Compton radius squared. And I would say that this is the kind of more physically meaningful result. The alpha is kind of telling us what the likelihood is of light bouncing off of the particle. Because light is relatively weak, most of it doesn't immediately absorb from the particle, which is what we assume for the classical value. And there is kind of good reason from quantum mechanics to think about something like a point particle electron being spread out over a distance that is given by the Compton radius. Okay, so the size of the shadow of an electron, how much light is it going to absorb from a beam that's hitting it? It's going to go into simple harmonic motion, and simple harmonic motion things oscillate and therefore emit corresponding amounts of light. Okay, so that's really kind of leftover stuff. The other thing I wanted to talk about, okay, so let's, oh, that's because I'm presumably way up. Yeah, so here was the diagram we used for Rayleigh scattering, and this is talk of the spectrum of light. So notice that the cross-section of an electron didn't depend on the frequency, so it would be the same as high frequency and low frequency, and it turns out that at really high frequencies, where we're talking about gamma rays having energies comparable to the mass of an electron, then the shadow of the electron decreases. And all of this is nicely calculatable in good quantum electrodynamics. Okay, so we talked about all of this stuff. And this is what I wanted to talk about for the rest of the time. And it's again a case where I don't think we have time. I don't think you'd be informed by doing all of the vector identities that are necessary in order to produce this result. So first of all, what is the motivation behind? So first of all, I guess the name of this phenomena that we're talking about is the Maxwell stress tensor. And stress is a word that you probably haven't heard very recently since 191, but stress was a generalized idea of pressure, right? So if we're talking about pressure, if we had an area and pressure was a force that was pushing on that area, and the amount of that force was proportional to the corresponding size area we were talking about, and the proportionality constant was the pressure, and of course had the units of pascals. If you think about pushing your hand along a table, so we can again have a surface, but we can now be transmitting a force to the table that is not perpendicular to the table, not like pressing on the table, and that force is still going to be proportional to the area that we're making contact. So this is a more generalized idea of a stress. And finally, if we were sucking on the table, we could have a force that was pushing that way. So this is a tension. So we can have materials that are under pressure, materials that are under tension, materials that are under stress, and you probably spent a lecture talking about how materials respond to those using words like Young's modulus and shear stress and things like that. So this idea from pressure comes from thinking about materials, fluids, solids, that when we push on them, push on their surfaces, we get a corresponding response. Now Maxwell really kind of thought of the vacuum as something kind of like jello. And so jello could transmit pressures and tensions and stresses on the remaining jello. And you would see the jello respond to those stresses with strain, that is, deformation. So Maxwell was really pleased to see the same sort of phenomena present in electromagnetic fields, that there was something you could identify as forces through areas, magnetic pressure, magnetic stresses that are present. And let me comment in part why I'm talking about this, and that is just finished 200, and we wanted to talk about solar sailing, so we kind of invented out of whole cloth. Well, I argued based on relativity, which the students haven't seen, that if you have energy, you have momentum, in particular for massless particles, as you know from 370, the corresponding relationship, right, energy squared minus PC squared was the mass C squared. And if we're talking about massless particles like photons, then there's a relationship between the energy and the momentum. So we could talk about the momentum flow as being the S vector divided by C. Okay, so I don't know. That's it's an interesting argument, but it's not the sort of game we were playing with energy, right? So with energy, or charge for that matter, we said we've got some sort of container, and we had a conservation law to the extent that the amount of energy or mass that was inside the box could only change if we had a calculatable amount of stuff that was flowing in. So we had an equation that told us that if we integrated over the surface the S vector dotted with dA, that had to tell us what the time rate of change was in the volume integral of the energy density dV. And actually, of course, there was Joule heating loss, but we're at least currently ignoring that. So how would we run this same argument for momentum? So we would have to say that there is some momentum, say in the x direction, per unit volume of some container. And the only way the momentum in the x direction changed is because there was a flow of x momentum through the boundary of that material. And I know I specified the x direction, but this is of course also true of the y and the z directions. So what we have to have is not a scalar here, but a vector on both sides of the equations. So we're going to have some momentum density, and I don't know, here's the answer, and we're not going to do the algebra, so I guess that's perfectly good. And how do we deal with this flow? Right? We got a vector on this side, so we have to have a vector on this side. Currently, we just have a scalar, right, because we've got a dot product. So what we need is a matrix dotted into dA being integrated up around the surface. Okay? This was the only way we're going to get a vector out of this, and this is exactly the sort of thing we want, right? Because if we have some sort of area vector, dA, the force might be this way, might be that way, could be all sorts of different ways. We need to be able to change the direction of the vector quantity by kind of introducing this arbitrary matrix. And this, do a lot of vector algebra, you can find this conservation law, and this is the thing that is the matrix that you need to dot dA with in order to get what the momentum flow is. So, so this is kind of the final version of this result. If we, I think I briefly mentioned Einstein summation notation to you. If we have a repeated index, there's a sum. So this is really the T matrix dotted into ds. We integrate that up over the surface, and that's going to give us the total amount, the time rate of change in the total amount of momentum in the volume that's in the field. But of course, there also may be momentum change of the actual particles, right? And there is, because there's a force, right? The force is equal to the time rate of change in the momentum of the particles, and that's going to be QV cross B plus E, or more generally, it's going to be J cross B plus rho times the electric field. So this stuff has gone into it to look at the time rate of change of the momentum of the corresponding particles. Okay, so once we've got this stress tensor, we can talk about magnetic pressure. And of course, in general, there may be not just pressure, there could be magnetic tension, right, where the magnetic field is sucking on surfaces. There could be magnetic shear, where the magnetic force is trying to push it in other directions. We have all of those possibilities depending upon the precise form of this tensor. And I don't know, I'm told people better than me can kind of see the corresponding force by looking at the structure of the electric fields. So I don't know, we can certainly go a good ways on that. So first of all, notice, well, maybe I should write this a different way. So this is a dyadic, right? We talked about dyadics, just two vectors put next to each other. So if we were to look at the first row of this matrix, it would be EX, 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 EY, EX, EZ. And this is down the diagonal of something that looks a whole lot like the energy density with a minus sign. Okay, so let's talk about magnetic fields because the structure is the same for electric fields. But let's say we have a magnetic field that is parallel to the surface. So if it's parallel to the surface, that means that B dot dA is going to be 0. So these dyadic terms are going to drop out, and we're only going to have the diagonals with a minus sign. And so that says then that the force is going to be in the minus A direction. So this is going to be magnetic pressure. So when the magnetic field is parallel to the surface, it exerts a pressure, a force per area, on everything that's on the inside. And the same thing would be true of an electric field. So how about the other sorts of cases? So how about the case where, boy, I can't really draw this in 3 dimensions. So here's the area vector. How about if the electric field is in the direction of the area vector? And if you think about it, it doesn't really, it's not going to really matter whether it's in the direction of or whether it's in the anti-direction of, because everything depends on E squared, so the direction is going to cancel out. And under these cases, what you're going to have, we could work through the algebra, but it's a tension, it's a sucking. And of course, if we have in-between things, we're going to have in-between cases. So if we have our surface area vector and we have an electric field that's kind of at a 45-degree angle, then it turns out that we have a shear, a force that is parallel to the surface. Okay, so what's neat about this is, first of all, it means I don't have to lie about light pressure, right? Because now I know that light has momentum. I've proven the conservation law. Everything's good. I can see that the field theory has these properties kind of like Jello, and it turns out that every field theory has to have those properties. You have to have a stress tensor like this. And the other reason that I wanted to talk about it is if we think a little bit ahead to relativity, right? So then everything's going to become 4-dimensional. So in addition to momentum, we're going to have energy. So we're going to have the stress energy tensor, 4-dimensional thing. And it turns out that in Einstein's general theory of relativity, GR, the thing that is the source of the curvature of space-time is the stress-energy tensor. Right? So there are stress-energy tensors from material, right, like Jello, and now we can have stress-energy tensors from the electric field, and all of those things are the things that bend space-time. So the stress-energy tensor is the thing that's like charge. It's the source thing on the right-hand side of the ugly partial differential equation that runs GR. Okay, so I thought, so this is pretty abstract. So we do have momentum in the electromagnetic field. We have the stress tensor, the generalized idea of pressure at every point in space. And if we want the change in momentum of everything that's in a boundary, we just have to integrate that matrix ds to get the corresponding result. I might comment that the kind of next thing you should be thinking about is, okay, we've got conservation of energy, and we've got the Poynting vector, we've got conservation of momentum, and we've got the Maxwell stress tensor. About angular momentum. We could talk about angular momentum in the electromagnetic field, and things get pretty complicated. It's a very nice way to go, and there is angular momentum in circularly polarized light, as I've mentioned in the past. But typically this is a more advanced topic than I want to talk about. Okay, so I did want to kind of give you some ideas, some feelings about this stress tensor. So I've got some examples here. So what we have in the lower left-hand corner is a magnetic field from a wire that's going out of the page. And here we have an identical wire that's just across from it. And what we're going to be doing is trying to calculate the force on the left-hand wire by calculating what the stress tensor is on a volume that surrounds it. So kind of no surprise, when things are at infinity, they're going to go to zero. So we're mostly going to be interested in the stress energy tensor on this planar boundary. And it's kind of hard to see which way these arrows are pointing to get the total magnetic field. So I've blown up kind of this region of the diagram. And you can see that the magnetic field is perpendicular to the area. Incidentally, in the other side, it's going this way. But in all cases, it's parallel or anti-parallel to the area vector. And what we said is that made a tension, that made a sucking. So what this is saying, if we integrate the stress energy tensor along this boundary, is there should be a net force on everything that's inside of it that is in that direction. So is that the case? Do wires, parallel wires that are carrying current in the same direction, attract? That's what we have found the very hard way, because it's much easier to calculate the old-fashioned way. So if we look at just the wire on the right at the location of the other wire, it's going to be making a magnetic field like this. And you remember that the force is basically the current crossed into the magnetic field. And if I take that current and cross it into that magnetic field, yes, I do get a force that's in this direction. Okay, so that's what we said, that fields that are parallel or anti-parallel to the surface produce tension. They produce sucking. So let's take a look at the kind of opposite case. So now we've got a pair of anti-parallel wires, right? So we've got this wire here, the current is coming out of the page, and this one here, the current is going into the page. And what that means, of course, is at this location, I will have reversed the magnetic field, and hence I will have reversed the force. So what I'm hoping to see here is a magnetic pressure. And yes, lo and behold, you can see it gets pretty small when we're away from it, but along that surface, the magnetic field is parallel to the surface. And what we said is under those situations, you have a magnetic pressure. You have something that's pushing the thing that way. So those are, in my mind, kind of some neat and potentially useful examples of Maxwell's equations, which are the highlight for the course. And you can tell me how you like the course by taking a look at the evaluation link that I sent you earlier. Lots of applications of these guys, and we've just scratched the surface of them. And I guess since I've got 10 more minutes, let me very briefly comment about relativity, which would be kind of the next, to me, interesting topic. And this is not gravity, this is special relativity, just how things change at high velocity. So, amazingly, the equations that Maxwell wrote down 50 years before Einstein already included all of special relativity. Amazing. He didn't know it contained all of special relativity. He would have been, I'm sure, flummoxed by the paradoxes of special relativity. But it's all there. How kind of can we get it to work? How can we kind of see it working? So one problem is just counting things up. So we have 3 vectors, right? B and H, or B and E. How do we get these guys together? Well, so one thing pretty obvious to do is if we multiply the B by C, now they have the same units, so they could at least possibly be all together. So how do you fix 6 things into something that is 4-ish? Well, the answer is the field tensor. And the field tensor is a 4x4 anti-symmetric matrix. So we've got zeros down the diagonals, and what we have then are spots. The 1, 2 spot, that's a good spot for a 3 of something. And we've got the 1, 3 component, that's a good spot for a 2, and we have the 2, 3 spot, which is a good spot for the 1. And kind of the plan is to put magnetic fields, Z, Y, and X components there, and it's an anti-symmetric matrix, so we'll put the opposites of them there. We'll put the 3 components of the electric field there, and minus the 3 components of the electric field there. And it's going to turn out that if we dot this F with the 4 velocity, right, which is a combination of momentum and energy as it is, we get exactly the the Lorentz equation, the V cross B plus E corresponding force. Okay, so so that's how the fields fit together. How can we kind of make these sorts of equations? And the answer is going to be by, these things look like curls, but they're going to be divergences. So I'm going to use Einstein summation notation. So if I take the derivative with respect to 1, 2, 3 of this 4 tensor, that is to say, so I would take the derivative with respect to x there, take the derivative with respect to y there, etc. This is going to be the current density, which has 3 components that are current and 1 component, like the energy component, that is density. If there were a monopole density, then, well, okay, so I'm speaking somewhat qualitatively in all of this. Where we put the B's and the E's is kind of up for grabs. If we switch them around, we have the so-called dual tensor. And if we take the 4 divergence of the dual tensor, we would get the monopole current. And the monopole current is, of course, 0 because there is no, at least no known monopoles. So I don't know, this is, I guess, too fast to be understandable, but the upshots that I hope you'll remember is that E and B really go together into one object, an antisymmetric 4x4 matrix that is called the field tensor. So E and B are really one thing, and they transform into each other when you do velocity changes, the same way velocity in the x direction can get mixed up with velocity in the y direction if you do a rotation. And the 4 fundamental equations of Maxwell's equations end up being just 2 equations of the field tensor and its dual, taking basically the 4 divergence of those and either getting the current 4 vector or getting the non-existent monopole current 4 vector. Okay, so relativity is nicely in there, stuffed into, these 3 vectors are stuffed into 4x4 sorts of things in kind of an interesting way, which works, and which was all discovered before Einstein wrote down his mechanics. Okay, so I think I've used up nearly every available minute. Good luck on the final. So we're probably going to want to schedule some sort of help session or some sort of review session. Probably have already done this since I'm speaking in advance to the physical end of the course. The final will be similar to the other exams. I would usually say except twice as long, except you know that exam 2 was more than twice as long all by itself than what it was supposed to be. So we'll typically have, I haven't written it yet, we'll typically have probably 8 questions that'll hopefully be comprehensive and talk about everything that we've talked about and not be too dissimilar from the ones we've done for homework problems and for exam problems. So good luck. I will actually probably see you in my future because this is actually a week before this talk is scheduled to occur.